F1 and F2, let's find the expression for the net magnetic force. So in the x direction, sum of the forces in the x is F1 times cosine 60 degrees, because here's our F1, it's got an angle of 60 degrees. F2 points to the left, so the x component is going to be negative, minus F2 times cosine, its angle is also 60 degrees. If we look down at our expression for the forces, they're I3 times L times mu naught I over 2 pi r. So the magnitudes of those forces are going to be the same, so our net x components are going to be 0. And that makes sense because it's symmetric about that wire. Okay, let's do the y component as well. Sum of the forces in the y is F1 times sine of 60 plus F2 times sine of 60. Both are positive because both point up. So that's equal to 2 because F1 and F2 are the same. We've got 2 times I3 times L times mu naught times I over 2 pi r times sine of 60 degrees. And this I3L mu naught I over 2 pi r, that came from the magnitudes of those forces. So there's the sum of our y forces. We see that the 2's cancel, so that simplifies a little bit. I3L mu naught I sine 60 over pi times r. And this is our magnetic force, so that's the amount of field that points up. We know that the wire is floating. That tells us that the sum of the forces in the y direction has to be 0. So the magnetic force minus the force due to gravity or the weight has to be 0. So I3 times L times mu naught I sine 60 over pi times r minus mg equals 0. We're asked for the current in the wire, so let's solve for I3. We'll bring our mg to the other side. So I3L mu naught I sine 60 degrees divided by pi r equals mg, and then we'll just solve for I3. I3 equals mg times pi r divided by L times mu naught times I times sine 60 degrees. So there's the magnitude of current that will allow that to float, and the direction has to be out of the page so that we get the force in the right direction.